If it's odd, you want to multiply by 3 and add 1. In either case, take the resulting number and then iterate. So for example, if you start with 3, that's odd, goes to 10. By the mapping, that's even, cut it in half, and so on and so forth. And you see that this 4-2-1 pattern will just iterate forever. So the question is, do each of the positive integers eventually iterate to 1? That's the problem. I've explained it to each of my children when they were 7 or 8 years old. They worked on it for about a day and moved on. I haven't moved on. And I'll say something about the history of this problem as well. All right, so first, there's 2 or 3 different notations which are used in the literature. The old one is C of x, and this is just as I described it on the last slide. But we can compress the dynamics a little bit. If you start with x as an odd number, you get this, but if x is odd, you can see 3x plus 1 will be even. So you know your next step will be dividing by 2, so why don't we just divide by 2 right away, and that will compress the dynamics. So you can see this is the old iteration I had, and in the compressed dynamics, it just makes our life a little tidier. So any positive integer must iterate under this map T to one of the following. So and now instead of having 4-2-1, 4-2-1 forever, now it'll just oscillate between 2 and 1. That's called the trivial cycle. And we expect, that's the conjecture, that everything will eventually enter the trivial cycle. But there could be a non-trivial cycle, and I'll have something to say about that. Or you could have some orbit which marches off to infinity. Now it won't march off monotonically. You can show that any starting odd number has to hit an even eventually, and so it will come down. But it could kind of do this kind of thing and keep growing in the limit. I should say, so most of the papers that are written on this topic use the T form, the compressed dynamics that I just mentioned. A few papers still use that older notation. And then a very few papers use the most quote-unquote optimally compressed notation. You'll take an odd number. If your number is even, you don't just divide by 2, you divide by as many 2's as possible to get it down to an odd. And so people just look at the dynamics on the odd integers under this map. But counting exactly how many 2's will divide into it is not a neat process, and so it makes it harder to do analysis on. Okay, well, as you might have guessed, some people have looked at numerical investigations. I have some various records to report in 2000. I'm using 14.4 CPU years, just a little over 10 to the 17. So all numbers up to there were checked. Yes, they do iterate to 1 eventually. In 2003, there's a Dutch mathematician who set up a distributed computer project, and so people will come in and check a certain range, and he's gotten it a bit high, about twice as high. And then the same person who worked on this, he's gone quite a bit higher still. This took 81.1 CPU years. But if you're going to infinity, this still isn't very far at all, is it? So we still have a long ways to go.
Actually, when it was first up there, I was very impressed because I thought that you were going to say, if n is bigger than some number, like the Skews number, or some number we don't know it explicitly, then the conjecture is true.
I don't know of such a result. That would
now I understand large is
yes.
a matter of
large is all in the eye of the beholder. Yes. That's right.
And just by curiosity, when you start with numbers like that, how big do the steps get?
I'll show. Let me show you an example. So there's 3 expressions which are used in measuring what happens with the starting number. So don't read all this. Let me just describe it in lay terms. So stopping time means you start with the number n, and the stopping time is the number of iterations you need to get below where you started, the minimum number of steps. So if you started with an even number, the stopping time is 1, okay, because you will go down. The total stopping time of n is the number of steps it takes to get to 1, the minimum number of steps. And of course, if it never reaches 1, if the conjecture is false, then the total stopping time will be infinity for that starting point. And then the height is the maximum you hit before you come down. And even with a modest number like 27, it takes 96 iterations before you jump below 27, 111 iterates to get to 1, and you can get as high as 9,232. So this is part of what makes this problem so difficult, is there's not really nice constraints about what can happen on the iterates. They can really kind of seem to get out of control until they maybe start collapsing down to what we expect them to.
Could you just remind me, is t the one where you've divided 3x plus 1 by 2?
Yes, yes, and that's the one 96% of the slides will worry about. Okay, so just keep that mapping in mind. So the stopping time, and again, there's a lot of nomenclature on here. What is the take-home message on this slide? This statement is basically saying almost all integers have a finite stopping time. Almost all integers will get below where they started. Now that's not all, it's almost all in a density sense. So this is, I would say, probably about the strongest result there is on the 3x plus 1 problem. One thing that drives people like me bananas is that, as opposed to most other well-known conjectures that have pretty solid partial results at least, I feel the 3x plus 1 problem has almost no good partial results. And this, I would say, is probably one of the strongest, if not the strongest, partial results. If there was some kind of randomness going on, and this gets a little philosophical into the problem, because this is a completely deterministic problem, but people have used stochastic approaches to look at it and to see some kind of order. If there was some kind of, if you've iterated for a while and you've gotten so mixed up you don't know which way you're going, you have a 50-50 chance of going up or down at each step. If you reach that point, then with this kind of quote-unquote randomness, it takes approximately 9 to 10 steps to get below where you started. And this matches decently well with what is experimentally observed. So, you know, you would expect, all right, on average, it takes this many steps to get below where you started. If we could prove that all numbers had a finite stopping time, then by induction you would be done, because you get finite number of steps below and you just keep going down and you're done. Everything has to get to 1. But this is only assuming a certain kind of randomness is built in. The total stopping time...
So you have a heuristic proof.
That's right. There are heuristic arguments.
Because it looks pretty random to me.
Because it looks pretty random, that's right. But, and here again, Dora and I have to say, but it's not a proof, okay? So I said this yesterday.
It is a proof, not a formal proof.
All right, not a formal proof. The total stopping time, let me remind you, that's the number of steps starting at n. Sigma infinity of n is the number of steps you need to get down to 1, the minimum number of steps. And people have looked at what's this called gamma of n, the stopping time ratio. We're going to divide that by the natural log of n. And we can get some kind of bounds on this kind of thing. Log of 2 and log of 3 come up with some frequency for people who are trying to do analysis on this problem, not surprisingly, because we're more or less multiplying by 3 and dividing by 2. Rn is the ratio of the number of odd iterates versus all the iterates we've gotten up to a point. So we've got something, there's a lower bound and there's an upper bound for this stopping time ratio. So something times log of n kind of makes sense for the total stopping time. But again, we just have these kind of rough heuristics going on here. More specifically, this is what I was saying a moment ago. Suppose you had roughly a 50-50 chance of going up or down if you pick some large some large number and then watch what happens, then that ratio I talked about theoretically is exactly this value. It's been shown with stochastic models that the limb soup of these guys is bounded by this quantity, and the closest that's come to it with this particular starting number, because people have done a lot of experiments, with this particular starting number, that's about the closest we can get to 41. So, and this is pushing kind of this randomness as far as I've seen people like Jeff Ligarius and Applegate have worked on this. Somebody called this a global statistic. Suppose I start at the value A1, and it takes me p iterates to get down to 1. So let's label these numbers A1, A2 up to AP, and we'll create this expression here. Notice it's a quadratic polynomial of the a's on top and on the bottom. And the authors were able to prove that this ratio, no matter what you start with, has to lie between these two fractions, which are relatively close. And these bounds, the lower and upper bounds, are sharp because if you start with either of these particular starting numbers for a given k, as k or n tend to infinity, you approach the lower bound or the upper bound. But, you know, this is a pretty tight gap here, so it's suggesting there is some order going on here. There is some order in the total stopping time. Maybe there's even better quote-unquote global statistics out there. Let me talk about the origin of this problem a little bit. So it's traditionally credited to Lothar Collatz. He was at Hamburg. And Collatz apparently was interested in graphs, graph theory problems, and he was looking at various graphs and directed graphs and looking at cycles within them. And he had a particular graph, and everything seemed to land in one cycle. And so he wanted to come up with something simpler. He looked at this particular function, which is similar in spirit to our t function, a little more complicated, and each of these expressions, depending on which modulo class you're in, works out to be an integer. And he saw that this seemed to be complicated, so he said, what is a simpler problem I can build, the simplest problem I can build that still captures the complex dynamics that he's seeing here? And that's when he got to this so-called 3x+1 function. So Collatz never published anything on it because, as he said, he obtained no results. And I would say join the club. There's lots of people who have worked on this and have gotten no results. But there are other names for this problem, sometimes called Haas's algorithm, Syracuse problem, because this problem made the rounds in different schools, okay? But it's got all kinds of different names. Thwaites is a little bit funny. Sir Brian Thwaites is a British mathematician, and he was a teacher in the 50s, and he claimed it was a hot summer day and his students were bored and he had to kind of keep them motivated. So he thought about this exact problem, the 3x+1 problem, and he gave it to his students just to work on, and they had fun before the class was over. So he claims to have originated it, and he can say the exact hour of a particular day, and so he claims to be the author of it. Nobody really thinks of Thwaites now. Everybody credits it to Collatz, but it didn't stop Thwaites from sometime in the early 90s writing a paper called My Conjecture.
How come Hasse got an algorithm, everybody else got a problem?
I don't know. That's funny. It's well, maybe Hasse doesn't have any problems. So,
Well, it's the number theory Hasse?
yeah.
Kakutani got input for
Yeah.
ergodic theory?
I think it's the ergodic theory. Yeah. So I mean, this problem kind of got
No,
around.
but Kaplan popularized it. He
Right.
never claimed to.
Not originated, but popularized.
where they
That's
had about
right.
it
So
from.
somebody would hear it, and there's
Ergodic
this.
theory.
He gave talks about it, I think.
Yeah. So Stan Ulam was the same. He didn't claim to have invented it, but he popularized it. So there's a funny quote about the popularization. For about a month, everybody at Yale worked on it with no results. Similar phenomenon happened at Chicago. The joke was made this problem was part of a conspiracy to slow down mathematical research. And to some extent, it's true. if you, keeping in line with Collatz's motivation, there's the so-called Collatz Graph, and this is a sketch due to Collatz. And you can see he's writing in German here, 3n plus 1 for ungerade, for n odd, and half n for n even. And he's got his little kind of tree here, or graph, which he's generating. A cleaner portion of that can be written like this. But of course, you know, this tree is going on forever, and so you need a very
So he's actually iterating it backwards.
Right. So and here you see the cycle, and he's using the C map that I talked about on the first slide, and he's generating it backwards. And he was interested in our magic 27 that I talked about, and you see it got so much, he's got dots in here and so on, and eventually it comes down. All right, predecessor sets. So one significant piece of analysis that a German mathematician named Gunther Welsching worked on, he looked at what are the so-called predecessor sets. So again, let me try to say this without worrying about all the notation. With a number A, what are all the numbers above it which will eventually hit A? That is, if you made the graph, like I had on the last slide, what are all the branches and leaves above that point? So that's the predecessors of A, and then this Z sub A of X is the predecessors of A which are below a value X. And at some point, some people started looking at Z sub 1 of X, that is, what are the numbers which iterate to 1 but are below X? And the question is, could we get this greater than or equal to X to the C for some positive variable C? And in 79 it was shown there exists a positive C so that this holds for X sufficiently large. And then in 90 it was sharpened that I can get an exact value of C, 0.25, and then higher and higher and higher, and this is the best that I know of to date. So we're trying to get these, again, it's like saying how much of the tree do I know will be coming down to 1. And
So you see it's 1, then you prove it? That's
well,
eventually.
I guess so, yeah. I mean, you
Wow.
can't get C equal, yeah,
For sufficiently
well,
large,
C
right?
equals 1 for sufficiently large, yes, that would prove it.
So you do have partial results, isn't it? Okay.
Yeah, but 0.84 is kind of far away from 1. Yeah, we think it's close to 1, but it's still, to me, this, in a certain sense, is no better than the density result I mentioned earlier. Okay, some people have tried looking at the problem by reducing the problem to different residue classes. So if I can prove the conjecture, if I start with numbers in certain residue classes, would that be sufficient to prove it for all starting numbers? So obviously, if I prove it for all odd numbers, I will be done. If you do it for 4k plus 1, numbers congruent to 1 mod 4, you'd be done. 4k plus 3, this guy. And for any j, you can prove this guy. And since I can make this j as large as I want, I can get the density to be as small as I like, but still all of these have positive density. So a question which hung around for some time was, is there some set of zero density which would be sufficient? If you can prove 3x plus 1 on that set, it proves it everywhere. And so here's a zero density type result, but it involves a different function, a more complicated function. So this function R of n says if 11 divides n, then just return n over 11. If 15 divides n and none of the above, and not this case, then do this to it. And you have this finite number of branches that come out. So it's a much more complicated function. But the claim was the 3x plus 1 conjecture is true if and only if the orbits of this function, if you start at any power of 2, iterates to the number of 2. And since this set has zero density, then this is like a zero density result. If I can prove that the R orbits of any power of 2 eventually gets to 2, I would be done, and this set has zero density. The problem, though, is that this is a much more complicated function to evaluate. If you start with 2 to the 3 equal to 8, it takes 50 iterates to get down to 2. So whether this is really helpful is not really quite clear. What's helpful with this approach, though, I'll point out, is it gets rid of that +1 part, 3x plus 1. The +1, is just a pain in the ass to deal with, all right? You try iterating it, and if you didn't have the +1, you're just multiplying by 3's and dividing by 2's, and you've got some structure you could deal with, but that +1 just creates a lot of headache. This, at least, you've gotten rid of the +1 part, but all these nodas create problem with analysis. So, all right, let's move on. Let's talk about cycles. Remember I said earlier that we have 2 options. We either approach the trivial cycle, 1, 2, we approach a non-trivial cycle, or we approach infinity. So let's talk about cycles. So suppose I have a cycle of points. That is, I start at one number in the cycle, and after a finite number of iterations, I come back to where I start. If I divide it in the even number of terms, the even terms and the odd terms in the cycle, here's a cute little exercise. If you want to feel like you're making progress on this problem, this is not hard to prove, okay? But it takes a little bit of thought. If you sum the even terms in the cycle, it's equal to the sum of the odd terms plus the number of odd terms. And there are other results. If you have a cycle, then you must have some integers and be able to express a number like this. The only circuit is the trivial circuit. A one circuit means you just go up and you just come down and you're done, and you've entered a cycle. A 2 circuit means you go up and down, and then you're back to where you started with. So it's been shown this is the only 1 circuit. There are no 2 circuits, but there's lots of other stuff to worry about. Other stuff with cycles. So this is all, I would say, another very interesting, helpful result related to the conjecture. So if you had a cycle and the smallest term was m, small m, and the largest term was capital M, then you can bound the total number of terms in the cycle divided by the number of odd terms by these 2 quantities here. So this tells you if you had a large cycle, if the terms were very big in your cycle, this tells you that this ratio is approximately log of 3 base 2. This is an irrational number. And so people have used Diophantine approximation to say, what can I say about this ratio? And it forces the number of terms in the cycle to have different forms. This was a result in 93. This was a stronger result in 97. And these forms, which were generated, were based on the lower bounds for, if I have a cycle, I showed those numerical computations from before. So the numerical computations help generate the size of these numbers. If we have even higher lower bounds, it's going to give even bigger numbers coming up here. So amongst other things, this tells me if I had a non-trivial cycle, the length has to be at least 272 million long. So if some of you are trying to scribble to find an example on the back of an envelope, you need a pretty big envelope. Okay. All right, the problem has had a lot of allure. That's none to say. Paul Erdős said, mathematics is not yet ready for such problems. And he's quoted as other people have asked him about it after such quotes, and he would say things like, oh, it's hopeless, absolutely hopeless. And
He refers to such problems as diseases.
really? Yeah. Well, I know of people who have really consumed a lot of time on this problem without really getting too far. So, myself included. Okay. There are prizes, okay? So, especially if there are students in the audience. Now, you are aware, like the Clay Math Institute has some prize problems, things like for the Riemann hypothesis, P versus NP, existence of solutions to Navier-Stokes equations. But you may not know that there is prize money for the 3x plus 1 problem. English offered $500 himself, and remember Sir Brian Thwaites, he offered 1,000 British pounds. Now, the first two have passed away, and I'm guessing the third one has by now, so there might not even be any money.
I think Ron Graham has.
Ron Graham said a long time ago he would honor Paul Erdős's, but I don't even know if he still does that. So don't hold your breath. Okay. All right. There's a so-called weak 3x plus 1 problem. So you start with, you build a multiplicative semigroup that's generated by these fractions here, and of course you see the 3 and the 2, it has that 3x plus 1 smell to it. So you take these numbers, you build a multiplicative semigroup. The weak 3x plus 1 problem says that the set S contains every positive integer. And it's been proven that the 3x plus 1 conjecture implies the weak 3x plus 1 conjecture. I hope the graphic helps you see what I think of as the relative strengths of these two different problems. And the weak 3x plus 1 problem was proven in 2006. All right, well, at least it's not false, because that would imply this is false, and nobody believes this is false. So what do you do when you can't prove something? Well, some people, including myself, have tried to extend the problem to larger spaces. So instead of just working on the positive integers, what if we just look at all the integers? Keep the same map, but now you're just allowing it to work on all the integers. And you have 3 new cycles. You have this very simple one, you have this with 3 terms, and this one with a few more terms. And it's conjectured that there are no other cycles on all the integers besides these 3 and the one with 1, 2. And that's it. And I'll just point out that going to the negative integers, working on is equivalent to looking at the so-called 3x minus 1 problem. And I'll talk about that kind of thing in a moment or two. Extending beyond the integers, a few people have looked at the ring of 2-adic integers. And so you've got the same kind of map as before. And it's shown that from a dynamical perspective, this map is conjugate to a shift map via this conjugacy. And I don't want you to get stuck on that too much. But there's been some interesting work to do with looking at this conjugacy. And now, if you look at rational numbers whose in reduced form, who have odd denominators, it ends up that the 3x plus 1 problem is equivalent to these other kinds of things. So some stuff with this 2-adic analysis have been studied, but as far as I understand, it's kind of come to a standstill for several years now, and not more progress is being done. But this is a reformulation in a different sense. How about extending it to the whole real line? This is from a paper that I wrote in the mid-90s. So my idea was, we know that when x is even, I divide by 2. When it's odd, I want this expression. So I'm going to interpolate this branched function with cosine and sine. And so on the integers, I get exactly what I want, but I've got a function that works off the integers as well for any real number. So this map has certain interesting properties. The reason I wanted to do this is because there's a lot of, it's a well-developed area studying real dynamics, and I thought I can use the tools of real dynamics to help me get some information about the iterates of this mapping. So any cycle in the positive integers you can show is locally attractive. If you have a cycle close by, real numbers have to get sucked into it. It appears to be only 2 attracting cycles. There's the trivial cycle, and then there's this other funny 2 cycle which is off the integers. For people who know dynamics, this map has what we call negative Schwarzian derivative, which is important. It means that we only need to be looking at the critical points of this function to understand the long-term dynamics. And indeed, I could show that the 3x plus 1 conjecture is equivalent to showing that the critical points of this function all iterate to 1, 2. Unfortunately, there are an infinite number of critical points, so is this any easier than studying the original problem? I did some more analysis, and I maybe in the interest